This is going to be over section 15.2, equations of state. It'll be a little bit longer than some of the other lectures. So what we are looking at here are physical quantities of a gas, such as pressure, volume, and temperature. And although the material can be in gas, liquid, or solid form, we'll most likely limit our analysis to the materials in the gas phase. The primary variables that we're going to be looking at are the ones that I had mentioned with the addition of quantity. These are sometimes referred to as state variables or state coordinates. The quantity of gas atoms can be specified by the total mass of the gas or by the number of moles of gas atoms contained in the volume. Just kind of depends on how you need to do it. So the volume is going to depend on pressure, temperature, and the number of atoms. And it's going to either be measured as the total mass or the number of moles. And ordinarily, we can't change one of these variables without causing a change in the other. In other words, when a sealed tank of oxygen gets hotter, the pressure is going to increase. If it gets too hot, then the pressure may cause it to explode. So when you change one variable, you're going to change the other. So for most non-ideal gases, the relationship among all of these variables can be expressed as an equation called the equation of state. If the relationship is too complicated for that, we can use graphs or numerical tables. Even then, the relationship among the variables still exists. We just may have to alter the equation a little bit. In this discussion, we're only going to consider equilibrium states. In other words, states in which the temperature and pressure are uniform throughout the system. In our case, the system is going to be an ideal gas. In principle, when a system changes from one state to another, obviously a non-equilibrium state has got to occur in order for the transition to actually follow through. So in other words, when a gas expands, there must be a mass in motion. And if there's a mass in motion, then that requires acceleration and non-uniform pressure. Similarly, when heat conduction occurs, different regions must have different temperatures. And we'll assume that such changes occur slowly, that the system is always very nearly in an equilibrium state. So the ideal gas equation. Most gases at low pressure have particularly simple equations of state. We're going to look at a setup here to study the behavior of a gas. This is actually what we're going to be looking at. You've got a piston down here, which is able to change the volume. You've got gas that you can add in, and depending on whether you want to measure the total amount of mass or the number of moles, you've got pressure, you've got temperature, and you can change that temperature by heating the gas. So first, the volume is going to be proportional to the number of moles and thus to the number of molecules. That makes sense. I mean, the more space that you have there, or the more molecules you have here, the more space that it can take up. So you can see how this might be proportional to this. Second, the volume varies inversely with the pressure. So if you double the pressure on something while you hold the temperature constant, as well as the amount that you have in there, you end up compressing the gas to 1/2 of the initial volume. Boyle's law is where if you take the product of the pressure and the volume, you end up with a constant, as long as these other two variables are constant. The third thing here is that the pressure is directly proportional to the absolute Kelvin temperature. So if you double the absolute temperature and you keep the volume and quantity of material constant, then the pressure doubles. This is called Gay-Lussac's law, where if you have the pressure is equal to some constant times T, and you hold the other two variables constant, then you can see the relationship. If you throw all of these relationships together, you get PV is equal to nRT. This is the ideal gas law. R is going to be defined as the ideal gas constant. The pressure is going to be in pascals. The volume is going to be in meters cubed. N is going to be the number of moles, and T is going to be the number of kelvins. R is going to be a universal constant and is going to have the same value for all gases. And it does not depend on the mass of the individual gas atoms. You have the number of moles, so you have how many they are, but you have no idea how much any of them weigh. If you need to change this constant around due to the units here, this is another value. If you take the ideal gas law and you change the number of moles here to the mass total divided by the molar mass, you can substitute this in for N, and thus you have this particular equation. Also, if you take the volume, or if you take the total amount of mass and divide it by the volume, you come up with the density. And this relationship right here shows you how the density of the gas relates to the other variables. For a constant mass or constant number of moles in an ideal gas, this particular product is going to be constant. Obviously, if R is constant for everything, and this is made to not change, then its product is not going to change. And thus, this relationship is going to remain constant. So as you vary if you were to keep one constant and you were to vary the pressure, then you could tell what the new volume is going to be. And here, in fact, are some problems to talk about that. This bio application is also something very interesting to read. So when we deal with mixtures of ideal gases, mixtures being, take our own atmosphere, you've got nitrogen as well as oxygen. You also have argon and some other gases that exist. One concept you're going to need is the concept of partial pressure. In a mixture, the partial pressure of each gas is going to be the pressure that the gas would exert if it occupied the entire volume by itself. If you look at our normal atmospheric pressure, the partial pressure of nitrogen is going to be 0.8 times 10 to the 5th pascals. The reason being, nitrogen is about 80% of the air that we breathe. The partial pressure of oxygen is going to be about 0.2 atmospheres. The ability of the human body to absorb oxygen, it depends on that particular pressure. When you start to drop that pressure, say to 0.13, then the absorption starts to drop pretty sharply when you get to that point and lower. That corresponds to about 4,700 meters or 15,000 feet above sea level. You start getting down to 0.11 and the oxygen absorption is not sufficient to maintain life. That's why why you don't have settlements above 16,000 feet. Though you can survive for limited amounts of time. And if you go up to Mount Everest, that place is littered with oxygen tanks. And the reason is that the partial pressure of oxygen there is about 0.07. Also, if you fly at altitudes of 8,000 to 12,000 meters, you've got to pressurize the cabin. Otherwise, your oxygen is not going to be exist enough at a pressure that you're going to be able to continue to breathe. That's why you have the oxygen mask in case you lose pressure. So, PV diagrams. So, the equation of state is a relationship among the three coordinates, like we discussed up to this point: pressure, volume, and temperature. If you hold the temperature constant and you let the pressure and the volume vary, you can draw a line that looks like this. Matter of fact, you can draw several of them. Depending on what the temperature is, the line will adjust accordingly. These are called isotherms, and the reason is isotherm, it's the same temperature. That's what it means. So the highest temperature is going to be the one that's furthest out here, just simply because your values for P and for V are going to be the highest along this line, followed by one that gets closer to these axes, and then closer still. You may have some situations here in which it doesn't obey the ideal gas equation, and at certain temperatures below a critical temperature, the isotherms develop flat regions where the material can be compressed without an increase in pressure. An observation of the gas shows that it's condensing from the vapor into the liquid phase. The flat parts of the isotherms here represent conditions of liquid, a vapor phase equilibrium. As the volume decreases, more and more material goes from vapor to liquid, but the pressure does not change. You can see that because it's a straight line here. It's the same value for pressure from A to B. To keep the temperature constant, we have to remove heat. So another diagram that is useful, especially for describing phases of matter and phase transitions, is instead of graphing pressure and volume, is to graph pressure and temperature. And this is going to be referred to as a phase diagram. Each phase is stable only in certain regions of temperature and pressure. Ordinarily, a transition from one phase to another takes place under conditions of phase equilibrium between the two phases. So for a given pressure, this occurs only at one specific temperature. And this is sort of what we're talking about here. Let's go ahead and let's take a look at this. So you got pressure this way, you've got temperature this way, and then you've got a sublimation curve. Remember sublimation, when you go from a solid to a vapor. You've got diffusion curve here, where you go from solid to liquid or liquid to solid, and vaporization from liquid to vapor or vapor to liquid. So you've got a vapor phase over here. So if you've got a certain pressure and a certain temperature, you might be over here, you could be up here, or you could be up here. So at T and P, values above the critical point, material properties change smoothly with changing P or T rather than undergoing a phase change. So along these particular curves here, you're going to see solid and vapor coexist. So solid and vapor are going to be here, solid plus liquid are going to be here, liquid plus vapor are going to be here. There's one magic point at which all three of these phases exist. This is the pressure and this is the temperature for that particular point. So triple point and critical point. The intersection point of the three equilibrium curves is called the triple point, which we just went over. For any substance, this point represents the unique pressure-temperature combination in which all three phases can coexist. We call this combination the triple point pressure and temperature. Triple point for several of these different substances are given here in this particular table. So figure 15.4, which I believe was right here, shows that a liquid vapor phase transition occurs only when temperatures and pressures are less than those at a point lying at the top of the tongue-shaped area labeled liquid vapor equilibrium region. This point corresponds to the end point at the top of the vaporization curve. In other words, here. And that's called the critical point. And the corresponding values of P and T are all called the critical pressure and critical temperature. The gas at a temperature above the critical temperature doesn't separate into two phases when it's compressed isothermally. Um, Instead, its properties change gradually and continuously from those that we associate with a gas to those of a liquid without a phase transition. Similarly, when a material is heated at a constant pressure greater than the critical point, the horizontal line above the critical point, its properties change gradually from liquid to gas-like.